Linear programming is one of my favorite Algebra 2 topics because of its extensive real-world applications. Linear programming is a method for finding a maximum or a minimum value of a system of inequalities known as constraints. The feasible region then is the solution or all the overlap of those constraints or inequalities. So it could be bounded like a polygon, or it could be open-ended. And an objective function is the thing that we are trying to maximize or minimize, and it will give the best combination of values to do so. The vertex principle is essential in linear programming. It tells us that at the vertices, that is where the answer must lie for a maximum or minimum value. What I'm going to do here is split up an example into two parts. So this is the first part where we're just going to create the graph and find the vertices of the feasible region. And then on the next page, we're going to figure out what the objective function is and then solve the problem. Usually, as you see here, it's just one big paragraph, and so we're going to work up to that level of difficulty. So I have the graph here for convenience. I will talk about how to create it. First, we need to figure out the system of constraints. So looking at the problem, I'm going to scan through. I need to come up with themes. I have breads A and B. Batch A uses 5 pounds of oats, 3 pounds of flour. Batch B uses 2 pounds of oats, 3 pounds of flour. And the company has 180 pounds of oats. Well, in the real world, we don't have an infinite supply of quantities, so that's why this is going to be known as a constraint. And it's an inequality because we don't have to use all the pounds of oats. So our first thing to mention here is because we can't go negative, we'll say that we have the amount of oats and flour is always going to be greater than or equal to 0. In a system of constraints, it is essential to restrict things to the first quadrant if that's relevant to the problem. Now let's dig into the oats. So I have 5 pounds from batch A plus 2 pounds from batch B. And we could use no more than 180 pounds. Scouring the rest of the problem, we see that another theme is pounds of flour. So we have 3 pounds of flour from batch A, 3 pounds of flour from batch B. And how much do we have on stock? In stock, 130 pounds of flour, 135. So that is our system of constraints, which I pull together using a brace because it's all together. And now, how do we get from the system of constraints to this graph here that then allows us to find the vertices of the feasible region, because the vertices are the reason why we're graphing, and the vertices will tell us what our best option is here for making different batches of bread. So, on one hand, you need to find the x and y intercepts. So let this be red, and then to find an x-intercept, you substitute in 0 for y, which is, if we're thinking alphabetically, the y will be the b, the x will be the a. So then the x-intercept of this inequality is going to be 36, 0. So you just substitute in 0 for this one. That then leaves us 5a equals 180. And then the y-intercept of that inequality, substituting in 0 for the x, gives the order pair 0, 90. Repeating that process for the second inequality, we find the x and y-intercept, 45, 0 and 0, 45 respectively. So we plot those points. So that brings us, with the red inequality, we plot the y-intercept here, the x-intercept here, we connect the dots, So that keeps us in the first quadrant. And then for the other constraint, we plot its y and x intercepts, connect the dots. Now about the shading, let's talk about that from a previous video that we did. You need to understand that because the dependent variable's coefficient is positive and it's less than or equal to, that will always be the case. So then we are shading down. And then we have the same deal here, positive for the dependent, and then less than or equal to, so we're shading down. And then in purple, here's where they overlap. So that's known as the feasible region. So any point in that feasible region will satisfy this whole system of inequalities, meaning that all inequalities will be true at the same time. However, we're not just going to be happy with making a workable batch of these two types of bread. Instead, we want to, as we'll find in the next example, maximize our profit. So we are going to, by the vertex principle, now rely on these 4 vertices that I've pointed out in green. And how do you find those? Well, the intercepts and the origin are freebies. But make sure that you pick the right intercepts, because there are other ones, but they have to be along the boundary of the feasible region. Now this one here, what I would recommend is to use the calculator instead of solving it with algebra, substitution or elimination. You will want to take this and put it into y equals form. So you would put it into the y1 slot on your calculator. You could let the calculator do the math, so you could put in like 180 minus, now remember a is x, so 5x. You could put the cursor back here and you could hit second insert or second delete, and that does insert, and then you could put in a parenthesis, and then you could put the cursor back over here, close that parenthesis, and then hit divide by b's coefficient, which is 2. It doesn't have to be simplified because the calculator will do all that for you. It makes no difference to the calculator. But for my purposes here, I am going to simplify things. Notice that is the y-intercept, so we're in agreement there. And then for the second inequality, you would have that going into the y2 value, simplified, gives you negative x plus 45. Now there is a neat feature on the calculator. I don't use it because, again, like, we know how to graph inequalities, but if you do want to check yourself, you can realize that, yeah, okay, so I isolated the y variable, the dependent variable, and in the process the inequality didn't change. So I would be able to move my cursor to the left of the y2 and hit enter until I get this lower left triangle to appear, and that will mean that it's going to shade down. And then we could do the same for the one above it. And then when we hit second graph on the calculator, well, we're not going to see anything because we need to change our window. That is an essential skill to look at the context of the problem, realize that we have intercepts ranging from 0 to 90. So let's take a look at adjusting our window. You press the window button, and then for the x min, it would make sense to put that at 0. And for x max, well, we have x-intercept of 45. That's larger than the one of 36, so we want the whole graph to be on the screen, so let's go with 45. And I like to give a little perspective and go a little beyond, so maybe 50 would work. And then y min, also at the origin, and y max, the larger of the two x-intercepts, is 90. And I'll give a little perspective and put 95. So then I hit graph. Don't hit second. Don't hit zoom 6 for standard viewing window, because that would then remove all your adjustments to the window. And then you should get a graph that looks something like this. Then you would hit second trace, 5 for calculate, and you would go ahead and figure out that order pair of 3015 with the help of the calculator. So what's next is to take these 4 vertices and in the objective function figure out which one produces the most profit. Now let me level with you for a second. Because I split this problem up into two examples, I didn't really go in the order that you always will. What you need to know is the first thing you do is figure out what you are trying to maximize or minimize. That goes with your objective function, which you want to write first, so you don't accidentally put the information into your system of constraints. So you scour the problem for that word maximize or minimize, and then here, because it's profit, that means the objective function is going to be, P makes sense, profit. Okay, so anything dealing with dollar signs, that makes it really easy. So batch A yields a profit of $40. So however many batches of A we make, we get $40 for each one. And then we're going to add that to, let's see here, batch B yields a profit of $30. So then that's going to be 30 times B. And that's the objective function. And I would then cross that off before making my system of constraints, so then I don't put the money information in that system. Now I need to remember what my vertices of the feasible region were. So the vertices I'll record here for us. They were 0, 45, 30, 15, 36, 0, and 0, 0. Now, I know you could probably guess that this intersection is going to maximize your profits because you have common sense, but you still need to check. So the way you do that is then by evaluating the objective function. And you make a table just to keep track of your calculations. So there's the rule for the function, profit, and you substitute in the values one at a time. So I have the ordered pair 0, 45, netting a profit of $1,350, and then I substitute in 30, 15, giving 1,650. Substituted in the next ordered pair. And the last ordered pair. Showing all my work, but of course when it's 0 you don't have to write that product. And lo and behold, this does maximize the system. So the answer is I need to make 30 batches of A and 15 batches of B. And that takes into consideration how many oats and how many pounds of flour we have on hand. And it also takes into account the amount of money that we could charge for each of those batches of bread based on, I guess, cost of ingredients and how much like supply demand and how much customers like it. So this is a real world example of using inequalities, finding the intersection of lines, substitution, elimination, or with the advent of technology, the calculator. Let's see here. And evaluating functions. This is also tying in that content that we've been learning on a real world problem. So now we're going to look at another one from start to finish. Again, I have the graph here, and this one's a little more complicated because things in the real world aren't always square or circular. So let's dive in. Remember, the first step is going to be to find the objective function. So I need to carefully read the problem and pick out when it says maximize or minimize and use that information only for the objective function and not the system of constraints. So Sue manages a soccer club, sending members to a camp, $75 for an advanced player, $50 for an intermediate. She could spend no more than $13,250. She must send at least 60 more advanced and intermediate. Minimum of 80 advanced players. Okay, I see the word minimum, but not minimize, so I'm going to keep going. Find the number of each type of player so you can send. Oh, yeah, she wants to maximize the number of players to go because that would make her team better. All right, so there's the word maximize, and it's number of players. Ugh. These are harder because, well, there's not much said, or if anything, about just like straight up players. So that being said, for step 0, as I'll call it for the objective function, it's kind of like the initial pre-step of the problem. The objective function then is very simple. So if you find yourself kind of stuck, number of players, P, is going to equal simply X plus Y. Well, let's see here. X will be advanced because that's the first thing we came across, and intermediate will be Y because that's the second thing we came across. Don't make it difficult. But yeah, it didn't really say anything about either. It's just a total amount. We're going to have a certain number of advanced X and a certain number of intermediate Y. So it's an X plus Y rule. It's very straightforward. Don't let the simplicity throw you off. Now, let's go back through the rest of the problem and figure out our system of constraints. That'll be the next step. So I see dollar signs. So that means 75 for advanced, 50 for intermediate with a budget of 13.25K. So let's write that down. I got 75 for advanced plus 50 for Y and can spend no more than $13,250. Oh, you know what? I can't have negatives, but it does say right here that I have to have a minimum of 80 advanced players, so then that's going to be X greater than or equal to 80. It doesn't say a minimum about the intermediate players, so then I'm going to just make sure that's positive or 0. And this one is a little tricky. At least 60 more advanced than intermediate players. Well, let me throw a number out there. If I say I'm going to have 100 advanced players, well, it says I have to have 60 more advanced than intermediate. So what did I do? Well, I subtracted the one from the other. So that's telling me that the difference of the two has to be greater than 60. Takes a little practice. There's our system of constraints. What we do next is graph. So this graph needs some explaining. So the first thing that I would do is find the intercepts of this inequality. But here's the deal. This inequality has this purple line. Let me start color coding things first. So this one goes with the purple line. This one with the red line. Green. And blue. Okay, so the purple one, you'll notice the y-intercept is way up here. So that's going to distort my graph. So just kind of hold off on that one for a second and it'll all become clear. So I'm going to start with this one. And I realize that it's a vertical line. And then it shades to the right. And then this one keeps us in the first quadrant, so it's this one here. And then I shade up. So I'm starting to realize that all the action is going to happen over here. If there's a solution, it has to be somewhere over here. So then I don't want all this information over here. That's just going to distort the perspective of the graph. I want to highlight the salient features. So let me go with this one. Its y-intercept would be negative 60 all the way down here. I don't want to do that either. So for this one, I'm going to be a little clever. I'm going to find the x-intercept, which is 60, and then I'm going to use the slope. So it's going to be, when I bring this over and then divide everything by a negative, be positive x. So that way, it's direct variation in regard to right 1 up 1. As x increases, y increases the same amount. So I'll go over 20 up 20 so that I can reach the spot where it intersects the other inequality, because that's where the action's starting of the feasible region. And that's how I find that intersection, because think about it. I know x is 80 here. And if I put 80 into this and solve it, I get 20 for the y-coordinate. So that verifies that right 1 up 1 for 20 times will get me to that order pair. Okay, so the last, and so then you make array, starting at the x-intercept and through this point of intersection. This one here, little tricky. You want to put this equation into the calculator in y equals form. So that would look like, and so now you have this one in the calculator, and then you put this one into the calculator. Because I don't have that in front of me, I will show you how I really would do it. y2 is equal to, like, I don't know how any of this simplifies. You could divide it by 5 and go from there, but I'm just going to let the calculator do all the work. So parentheses, 13250 minus 75x, and then divide it by 50. Using the calculator's amazing ability to perform calculations. So I put these two into the graphing calculator, and I get this, and I get this. Make sure to adjust your window accordingly because, look, you're dealing with values in the hundreds. And then you find the intersection. Cool. So then you plot that point, cha-ching, and then, well, that's not too hard to find. That's an intercept. So that's where y is 0, so you would blank out that term and then divide that value into that one, and you would be on your way. I know it's a little tricky. You really have to think, and it's not a cookie-cutter approach, but it's not impossible either. So we then find that this is the feasible region. We find our vertices, and now we need to use them to finish the problem. So in order to help me do that, I'm going to clear this screen and make some room. So those vertices I have listed here, and now I need to substitute those in to the objective function. Instead of using a table this time, I'm going to show you what a bivariate function looks like. So a bivariate, like it sounds, has two inputs, an x and a y. So I'm going to rewrite as p of xy is equal to, remember our objective function was simply x plus y. And so now I'm going to substitute in those ordered pairs. So p of 80, 0 is literally just 80 plus 0, or 80 players get to go to camp. Remember, we're trying to maximize the number, so let's keep going. And then the next ordered pair, vertice, 80, 20. So 80 plus 20. And then moving along, 130 and 70. Thanks to the calculator for finding that one. Second trace 5 for intersection. And then that gives us, their sum is 200. Remember, I'm just using that rule, x plus y. And then last one. Yeah, so then this one maximizes. And so we should send, remember, x represented advanced players. And that means we should send 130 of those. And intermediate was y. And so we should send 70 of those. So linear programming is great, like most mathematics, because it extends our power of thinking. I don't know if I could just look at this problem and say, yeah, 130 advanced players, line them up, put them on the bus, and 70 intermediate. I know that's going to fit my budget, and I know it's going to meet the fact that I need to always send 60 more advanced intermediate, and I can't send a minimum of 80 advanced. Our minds don't work that way. So linear programming is a systematic way of being able to maximize or minimize a system.